but this is hotter than this is cold by 100,000th of a degree, 10 to the minus 5 degrees. So it's a very, very, very even temperature across the whole sky, but not perfectly even. And so there's fluctuations in the temperature that are very small, and they've been measured. And they're telling us a lot about the structure of what's going on in the past. And so people read these like tea leaves because they want to, it's telling us a whole bunch of information about the early universe. And the famous joke is that one of the things you see is that Stephen Hawking has written his name here. There's an S and an H. So that was an experiment that was done in the early 2000s. And it's been superseded recently, a couple years ago, by the Planck experiment, which measures this. And this just shows you that you're seeing real things. That the things that were hot here are hot here. The things that are cold here were cold here. And so the SH is still SH. And you can now see there's a bit of a W here because it's actually Stephen W. Hawking. So the resolution's a little bit better. So people look at that and they're trying to infer the properties of the universe. And there's a lot of information about the early universe there. And part of the information part of the evidence for dark matter and dark energy will come from the detailed properties of this microwave background. So what is the evidence for dark matter? Let's start off with that. So I'll start with the evidence, and then I'll give you a very quick judgment as to what I think is the most likely picture as to what it is. So again, there's got to be more than one line of evidence, and so there's several of them. The one you probably most often hear about is the evidence for dark matter in galaxies, that they rotate in a way which is not consistent with how they would have rotated if the mass of the galaxies was what you got by counting up the stars in the galaxies. So I'm not going to talk about that one because you've almost certainly heard about it before. I'll talk about the similar evidence coming from clusters of galaxies. Most galaxies come in clusters. They're all bound to each other gravitationally, and so you can ask how much mass is there in a cluster of galaxies given how the galaxies are moving, for example. I won't talk too much about this, but there's a story there. And I'll also talk a little bit about the, there's an argument for dark matter that comes from the picture of where galaxies came from. So here's a cluster of galaxies. Seen in visible light, these are galaxies. Not all of them, some of these things are foreground stars, but the big things are galaxies. And they're all the same distance from us roughly, and they're mutually gravitationally interacting. And so one way to get the mass in that cluster is to measure the speeds of these galaxies, which you can do by measuring their Doppler shifts, and seeing what the range of speeds is that they have around the common range they have. They all have a common speed, which is to do with the overall expansion of the universe, but then they all have a slightly different speed around that because they're moving relative to one another. And so that dispersion in their redshift is a way of measuring the amount of mass that's responsible for their orbits in that cluster. So that's one way to get the mass, and from that mass you find that the mass you need to account for the motion of these galaxies is in the ballpark of thousands times of the mass you get by counting up the mass of the stars that you're seeing there. Second way to get that same mass, because you want to have more than one way, so this one line of evidence is going to turn into like 2 or 3 lines of evidence. This is the same cluster of galaxies now seen with X-rays. And so what you see in X-rays is that there's a big X-ray source here, and it's not localized in any one of the galaxies. It's kind of really filling the space between the galaxies. And what that is that's very hot hydrogen gas. It's at 1,000,000 degrees or so. It has to be that hot to emit the X-rays. The sun doesn't emit X-rays. If you look at the sun with X-rays, it's not that bright because most of its light is coming out of visible wavelengths because it's in the 1,000-degree ballpark. But the 1,000,000-degree ballpark is something which is hotter than that. And so you don't see the galaxies in X-rays because they're like the sun. But this is very hot gas that's also in the same vicinity as the galaxies. And so it's being held there by the gravitational field of whatever's holding that cluster together. So another way to measure the mass of the cluster is to ask, how much mass would I need to keep gas this hot trapped? And you know the temperature of the gas because it's emitting X-rays, so you know how hot it is. And so the mass you get from that is similar to the mass you get from the motion of the galaxies, and it's kind of thousands of times what you get by counting up the stars. Turns out there's more atoms in the gas than there was in the stars in the galaxy. So if you're just counting up the baryons in this cluster of galaxies, you've got that wrong by factors of 10, just counting the stars too. But now you can see those. But what you need to account for the gravitational field is more than that again. So it's not the extra mass you get from the gas is not sufficient to account for the gravitational potential. But there's a third way to get the mass of a cluster like that, and that is by gravitational lensing. So if you look at a cluster of galaxies again like this one, you see these arcs. And what those arcs are galaxies that are kind of behind the cluster whose light is being lensed by the galaxies in the foreground. And so this is a simulation of that. This is supposed to be a uniform field of polka dots, which is moving from the right to the left, and there's a mass distribution in front of it, this pink thing. And this is showing you what the light would look like as it being lensed as it passes by these masses. And you see that the light that comes very close to the mass gets distorted into these big rings. And that's what these arcs are. That's strong lensing. But the light that's kind of a long ways away here is not these big sharp arcs, but it is distorted a little bit. These are no longer round. They're kind of more ellipsoidal. And so what people do is when they map out, they look at a field of galaxies, and they can statistically infer whether or not lensing is going on by looking at all these weak lensing events out here, the ones that are not distorted very much, by assuming that the galaxies are basically have no preferred orientation. They would have been arranged in all different kinds of ways. So if there's a preference for all the galaxies in some field of view to be lined up in some direction like this, that's evidence that there's a gravitational lens in the foreground, and you can use that to map out the stuff that you're not seeing in a cluster of galaxies. And that gives you the same kind of answer as the other two ways give you. So there's several ways of getting the mass of a cluster of galaxies. They all agree on what the answer is, and they all agree there's more than there is that you can account for with the baryons that are there. So this is, again, the last example is the bullet cluster, because it's a particularly nice example where you've managed to separate the baryons from the dark matter. So this is the bullet cluster. It's actually two things, this group and this group. They're believed to be moving, have passed through each other. So it's something which is believed to have been a collision. And the collision is believed to have happened because if you look at it with X-rays, like I told you before, you see this. You don't see the X-rays with the galaxies so much. You see them kind of in between. And that's what you would have expected if the galaxies passed through each other, because the stars mostly miss each other. They just go right through. But the gas interacts with each other, and it shocks, and it forms this kind of a wall in between. So that's consistent with them passing through each other. But if you look at that same thing with lensing, the way we just discussed, then you get this, that most of the mass, as far as the lensing is concerned, just did what the stars did, went right through and didn't stop in the middle like the gas did. And so it really is true that those are displaced from one another, the gas and the dark matter. So there's lots of evidence that there's stuff out there that you're not seeing gravitating in an ordinary way, but more of it than you would have accounted for from the atoms that you see. Another line of evidence for this is the story of galaxy formation. This is kind of a cheesy old simulation that's nowhere near as good as the ones that people make now. The picture here is we think we now understand where galaxies came from. And the idea is, you remember the microwave background was very smooth, to 1 part in 100,000, and the temperature was the same everywhere. But it wasn't exactly smooth. So gravity will act to enhance any initial inhomogeneity in the gas. If you have a little bit more mass here, that's attractive under gravity, so that'll attract even more mass, and that'll amplify the mass over densities. And then in a similar way, under densities get amplified. And so something which is initially very homogeneous, like this, under the action of gravity, will collapse. And that collapse is supposed to form the galaxy distribution that we actually see. Like this. And so the picture is that when you finally see galaxies arranged in these filaments, like you saw in the Sloan Digital Sky Survey, it's coming from a process like that. Starting with a very initial distribution, and you know it's initially very smooth because you know the microwave background is very smooth. And it gives you eventually the galaxy distribution that you hope that describes what you see. Now the reason that tells you that there's a line of evidence for dark matter here is because you know how much stuff, what the inhomogeneities were originally, you know how long it takes for them to grow to become galaxy. They have to grow long enough that eventually gravity can become strong enough to form a galaxy. And the interesting thing about that is that this process doesn't start until a particular epoch in the universe, which I'll explain right now. So out there in the universe, we got stuff. We got baryons, atoms that are moving slowly, they're non-relativistic. We have light, which is relativistic. Neutrinos probably that are relativistic. And as the universe expands, so this is the log of the size of the universe. So later is to the right. The amount of energy in this stuff, this is the log of the energy density, is falling. And it's falling for the atoms because the number of atoms is not changing. So the number of atoms per unit volume is falling because the volume is growing as energy expands. That's what this is, the matter. This is 1 over, this straight line is the power law, and it corresponds to 1 over the size cubed. That's the 1 over the volume of the universe. The radiation falls faster. It goes like 1 over the size of the universe to the 4th power because for a fixed number of photons, it's true that the number density of photons also falls like 1 over the volume. But then each individual photon's energy is being redshifted. And so that's why it falls faster. So originally, you'll have more energy in the radiation, but eventually, you'll have less energy in the radiation compared to the matter because it's losing energy. Its energy density is falling faster. I'll come back to this later on. This is what the vacuum would do. It's just something which just sits there and has a fixed energy density. Now, the thing you need to know about galaxy formation from the point of view of arguing that dark matter exists is that galaxy formation doesn't start until the universe has more matter in it than radiation, because the radiation moves too fast. It doesn't clump together into the galaxies. And so the start line is here. Galaxies can start here, and you can wait until, let's say this is now. Then what you can do is you can say, has there been enough time for initial inhomogeneities, which are only 1 part in 100,000, to grow into order 1 perturbations, which could be galaxies? And the answer is if all you have out there is the visible stuff, there hasn't been enough time for them to become galaxies. So if that can't be the right picture, if all you have out there is irregular matter. But if you had more stuff than what you see, then the matter would actually be something like this, still falling at the same rate, but there's more of it. So the start line now gets moved back to when it's the same as the radiation. And so now you've got more time to form the galaxies. And you can infer from this how much stuff you would need to give yourself enough time to make the galaxies that we see from what we know is the starting point when the microwave background formed. And what you get from this is comparable to what you get from looking at how much stuff there is in clusters of galaxies and these other lines of argument. So the upshot of this is that there's many lines of argument that say that there's stuff out there gravitating in an ordinary way, and it all looks like it's just dark stuff. And it turns out that there's more stuff there than there can be atoms, given that we have other ways of counting the atoms, since we know where nuclei come from. So what is that stuff? So here's the kind of the obvious list that if you had a Sunday afternoon and you had to figure this problem out, this is the list you'd make. The first thing is you'd say, well, it's probably just ordinary atoms. If you didn't know about the nucleosynthesis argument, you'd say it's dust, it's rocks or planets. And there's a variety of arguments that will bear on that. Second line would be to say, well, we're inferring the existence of this stuff from gravity. Maybe gravity doesn't behave the way we think it does. So can you modify gravity to make it all work and not have any new stuff? And the third line would be that there is new stuff and arguing about what its properties is. So here's where I'm going to give you my take, and this is just my take. My take here is the party line take, is that it can't be the ordinary atoms, and there's more than just the argument I gave you, but one argument is this one I gave you, that we think we can count the number of atoms from this nucleosynthesis story, and it's not enough to count for what we see for the dark matter. The modification for gravity, everybody would love to do this, because if you succeed at this, then 100 years from now, they won't be celebrating Einstein anymore, they'll be celebrating you, because you have the new law of gravity. So everybody wants this to work. I wanted it to work, but it turns out that, so because of that, it's been studied. It's not like no one thought of this before. It's been studied very hard, and there's two things that seem to be troublesome here. One of them is you can account for some things quite well. There's a modification of gravity that gets galaxies does a very good job of describing the rotation curves of galaxies. But that same theory does a really crappy job of describing clusters of galaxies. It doesn't have anything to say at all about the microwave background and a galaxy formation. And so there's no known, even though people have thought about it for a long time, there's no proposal that gets all the different lines of evidence. Right. And that's why it's important to have more than one line of evidence. In addition to that, it's actually really hard in principle to modify gravity without giving up things that we know we believe in even stronger than that relativity is right. It turns out that we now have a fairly deep understanding as to why gravity has the form it has, why the consistency of quantum mechanics and relativity, they want to be almost inconsistent, which is kind of a whole different talk, but it's I'm happy to answer questions on it later on if you want. But the relativity and quantum mechanics are almost inconsistent, but they're not quite inconsistent. And threading that inconsistent, what makes them consistent, it's difficult to make things consistent. And as far as you understand, general relativity is the only way of making a force which couples to energy consistent on long distances. And so that doesn't mean it's impossible to modify gravity in a sensible way, but it means no one's figured out how to do it, independent of the evidence for dark matter. The third thing is new kinds of particles, and this is actually easy. Every graduate student in particle physics makes a model of dark matter every Monday because it's something which is really easy to do. All you have to do to get this right, and to get all the lines of evidence right for dark matter, is to have a particle whose mass is like the particles we already know about, like the W boson, say, or the top quark. You have to give it an interaction strength which is similar to particles we already know about, like the weak interactions. So it can't interact electromagnetically, or we'd see it, but it can take part in interactions like the weak interactions. All you have to do to make this stuff dark matter, which the top quark and the W boson don't do, is to be stable, so that you don't decay before the universe, 10 to the minus 23 seconds into the universe. If you can make a particle like the ones we know about and make it stable, then the abundance that you get as the universe expands is exactly the right abundance to describe dark matter. And it gets all the lines of evidence right. And so if you have to bet money now as to what dark matter is, it's probably this, because this is easy to do, it fits everything we know about everything else about nature, and it gets all the evidence right, all the lines of evidence right, which the other alternatives don't. So that's my spin on modifying gravity, is that it'd be great to modify it, but the evidence doesn't seem to say that that's what's happening now. So that was the end of the dark matter story. I'm aiming for, yeah, so I'm aiming for about 10 minutes from now, right? 10. Yeah, okay. I'm gonna get there. All right, so what's the dark energy story? So the dark energy story, the main one will be, I have to repeat what I did for dark matter, and it'll be shorter because there's less evidence for dark energy. The dark matter evidence has been accumulating since 1931. The dark energy evidence has been accumulating since 1999 or 1998. And so there is more than one line of evidence, but it's there's not a whole bunch of lines here. And so most of what I say will be about those lines of evidence, and then I'll quickly, if there's time, give you my speech as to what I think is going on there. So what's the line of evidence? So the two main ones are these. So there's the first line of evidence will be to do with how the universe is expanding. The second one will be to do with the properties of the microwave background that I alluded to earlier on, and I'll say why. Okay, so what's the expansion argument? So when people found this evidence, they were not looking for it. They were trying to test Hubble's law. Remember, Hubble's law was the statement that galaxies move away from us with this nice rule that their speed is proportional to their distance from us. And I told you that that's what you would expect if they were not accelerating, if they all started here at the same time. And the key word there was if they're not accelerating. But of course they are accelerating. They're all interacting under gravity. Gravity is attractive. They should all be pulling on each other, slowing each other down. And so they should be moving slower than the strict law says. And the farther away you look at them, the slower they should be, because they've been doing it for longer. And so what people expect is that the Hubble law won't be exactly true, and it'll start to have deviations as you look farther and farther away from us. And so people were trying to test that. That's what their goal was when they did the measurements I'm about to describe. So what they did is, to test Hubble's law, you have to measure the speed and the distance. And so you have to have some way of getting both those things separately from one another. So you have to have something very, very bright, so you can see it across the universe. You can measure its speed by measuring its redshift. So you can measure how the light is being more blue or more red relative to you. But to get the distance, what you want to have is something whose intrinsic brightness you understand. So you can compare that to how bright it appears to be, because you know how intensity of light falls off with distance. And if you know how bright it appears to be, you know how much energy it was sending to you, you know what solid angle you intercepted, and so you can figure out how far away it had to be. And so what they use for that are supernovas. And so this is a picture of one of the supernovas that was found in the survey. And this is a galaxy, obviously. And this galaxy is a very distant galaxy. And you might have thought in this picture that this is a star in the foreground in our galaxy. And that's kind of what would normally happen in something like this. You'd have a galaxy in the distance with a star in the foreground. But this star, it turns out, is the same distance as the galaxy is. And you see that it's as bright as the whole galaxy is. And that's what a supernova does. That's why supernovas are so good to look at. A supernova is when a star is exploding. If you took this picture 6 months before or 6 months afterwards, the star is not there anymore. So that's kind of how you know that it's not a very bright star in the foreground, is partly, besides measuring its distance, is you look for them by seeing them appear and then disappear again. But when they're there, they're hundreds of billions of times brighter than a star normally is, and so they can compete with galaxies, and so you can see them across the universe. And if you believe that you know how bright they really are, then you can figure out how far away they are by measuring how bright they appear to be. And that's what people did to try and measure the speed and the distance to make this Hubble curve, to plot the speed versus distance and see if it's no longer a straight line. And so this is what they expected to do. So here again we have speed, here we have distance, and now the scale is bigger. I was showing you these points down here before. And what they expected to see was the curve going up. And that's a bit of a paradox, because what I told you is that gravity is attractive, so that they're all pulling against each other, so they should be slowing down. You might have thought the ones that are a long ways away should have been slower rather than faster. And the way to think about that is to think about the fact that when you look across the universe, what you're seeing is the stuff as it was when the light left. So the farther away you look, the older the thing is, because the light had to actually get from there to you. And so if things are all slowing down because they're pulling on each other, if you look to the most distant objects, you're seeing them as they were before they slowed down. And so because of that, when you look farther away here, you'll see them differentially faster than they would have been if you extrapolated the straight line that came from taking Hubble's law for the nearby objects and just applying it farther away. So that's what they expected to find. And of course, the reason I'm flogging this to death is that that's not what they found. What they found was this. So here's the same kind of a plot, speed against distance, and this is now in gigaparsecs, so this is a larger distance. These are the nearby ones. And this is kind of a big statistical mess. And these curves I'll describe in a second. These are different ways the universe could have evolved, but you can kind of see by eye that if you extrapolate the straight line, it's something like this black curve. And these points are mostly below the black curve, not above the black curve, which is what they thought we were going to find. So at face value, that says that things are doing the opposite of what I told you. The universe is not slowing down in its expansion. It's speeding up in its expansion. If you look at the distant things, they're going slower than you thought. So that means that they must have been speeding up as the universe is evolving. And that's a surprise, because the way I told you that they should have been slowing down was that gravity was always attractive. It's not like electromagnetism that sometimes it repels, sometimes it attracts. And so this is behaving as if something under gravity is repelling rather than attracting. And so this is the beginnings of an argument that whatever this is, dark matter won't do this, because dark matter was gravitating like everything else was. So this is a funny thing to have found. Now what these curves are going to quantify a little bit what you would need to get the universe to behave in this way. So I'll come back to what those colors are. So this is the same plot again. And so what this is now is a plot of dark matter in these units where its density of dark matter, where 1 is 10 to the minus 29 grams per cubic centimeter, like before. And this is some hypothetical thing which would repel under gravity. And I'll come back to exactly what the hypothetical thing was. It's going to be what the vacuum would have done if it was gravitating, it turns out. But it's a very specific rule for how things can gravitate in a way that would make the universe repel. It turns out that's not completely crazy. You can make the universe repel under gravity, or things repel under gravity. But I'll come back to what that choice was, but there's a specific choice you could have made. And this is the same units. This is the density of that stuff, where this is 10 to the minus 29 grams per cubic centimeter. And these different dots are different choices for the relative abundance of those things. And this is what they would have given you as the Hubble law if you worked out the cosmology for those choices. So these ones, the red one and the black one, are the ones that have no dark energy, this stuff, and only different amounts of dark matter. And so those are those two curves. You see the black one is better than the red one. So that's kind of more or less that one. The ones that do the best job here by eye are the green one and the purple one. Those are those two. And here's the blue one, which is kind of down below on this side. What the ellipse is here is it's statistically, of course, there's a big scatter here. If you kind of ask statistically what's the best fit to these data points, it's this ellipse here. So you want to live in the ellipse. You'd love to live up there, but anywhere in this ellipse is acceptable from the point of view of the statistics. And I want you to remember that, because I'm going to come to some other lines of evidence, and we're going to compare what they say to this to see if they're consistent. So what's the second line of evidence? Second line of evidence, we go back to the microwave background. You remember this is this snapshot of what the hydrogen was doing at the time when the universe became transparent. So this is a hot area, that's a cold area. What you're looking at there are sound waves in hydrogen. You know a lot about sound waves in hydrogen. In particular, you know what the speed of sound is in hydrogen. It depends on the density of hydrogen. And so if you know how many hydrogen atoms there are, you can figure out how far a wave could have traveled in the time that it had available to itself when the universe was that old. And that's comparable to these distances here, that distance to that distance. The typical scale of these fluctuations is being partly controlled by how far sound can go in hydrogen in the time available in the 100,000 years the universe has been around then. And so that's amazing, because somebody has now held up a ruler for you on the other side of the universe. So we're here. That wall is where the universe became transparent. And light is coming to that wall. It's a hot wall. It's got some hot areas and some cold areas. We now know the distance between the hot area and the cold area is the distance that sound can travel in hydrogen, which is a physical thing which we can calculate as a function of the density of hydrogen. And so if someone tells you, so now we have a ruler on the other end of the universe that we're looking at, we can infer a lot about the properties of the universe in between us and that ruler just from geometry. And in particular, we can measure if the universe is flat, the space is flat between the wall and here. And if we can figure out what the curvature of the universe is, since Einstein relates the total amount of stuff out there to the curvature, we can figure out the total energy density in the universe. And that's what I've been telling you has been done. And this is how they did it. So we'll look at the hot versus cold areas, and we'll make a triangle out of them. So we're here. This is the hot and this is the cold area. And this is a distance which is set by the speed of sound in hydrogen, which is a known thing. If we knew this distance, which we think we do, because that's the size of the universe, that's set by the expansion rate of the universe, that's set by the Hubble constant in the Hubble law, then for a triangle, from high school, you remember, or graduate school, or PhD, whatever, if you have two angles, and if you have two sides and an angle, then you're done with the triangle, right? That the Euclidean geometry will only allow you only have a certain amount of freedom. But when we measure a hot area and a cold area are separated by some angle, we're measuring this angle here. We think we know this distance, and we think we know this distance. We have too much information. This triangle doesn't have to make sense if it's not Euclidean. And so if light is traveling in straight lines, like it would in flat space, there's a consistency condition that this angle has to be consistent with this distance and this distance. If it's moving along the surface of a sphere, then these lines wouldn't have been straight. They would have bulged out because it's a line with a sphere. And so this angle for given distances could be bigger. If the surface had been like a saddle, for these fixed distances, this angle could have been smaller because the lines would have bent in. But by measuring the angle between the hot and cold areas in the microwave background, and comparing that to the distance that sound can travel and the size of the universe, you can figure out if the universe is flat or not. And it turns out that the measurements say that it's consistent with flat. And that can only happen if there's 10 to the minus 29 grams per cubic centimeter in it as total amount of energy density. And so you can subtract off the atoms, you can subtract off the dark matter, and what's left, if there's anything left, would have to be, you can ask, is that consistent with what you saw, what you would need to make the universe accelerate? And this is what that says. This is the same thing. This is the amount of dark energy, amount of dark matter. Here's what we saw before, what you needed to get the universe to accelerate. This is the line of a flat universe. And this is a line that the microwave background accepts as a allowed region. If you did not know the Hubble scale, the size of the universe, if you know the Hubble scale, you have to live in this region here. This green thing turns out to be, we had various lines of evidence for dark matter. I spent the first half of the talk talking about it. That's more or less a vertical line here. This is not exactly that, but it's almost that. It's essentially about the evidence for dark matter, and how much dark matter there should be. And you see that they all agree on a sweet spot here, that there's a consistent picture if you have this much dark energy, that much dark matter, and that's the pie chart that you saw. It was 70% dark energy, 30% dark matter, 25% dark matter, and a sprinkling of atoms. And you can get rid of any one of these measurements. Get rid of the blue ellipse, the other two still put you here. Get rid of this line, and these two will still put you here. And so that's the redundancy of the dark energy story. So that's how that pie chart came about. And so you can judge for yourself how convinced you are. The dark matter is more convincing than dark energy because there's more lines of evidence. But it's relying on the fact that there were more lines of evidence. And whatever it is, that stuff can't be the atoms because